Section: Introduction. In this section, we will discuss the use of pre-trained language models, PLMs, like BERT or Roberta for natural language understanding tasks. While these models are effective when fine-tuned with a lot of labeled data, deploying them for real-time applications can be challenging due to their large size and high memory requirements. Recent research has shown that only a subset of the model's parameters significantly impact task performance. This insight allows us to compress the model by removing less important parts without sacrificing performance. There are two main approaches to pruning: unstructured pruning, which removes individual weights based on their importance score, and structured pruning, which removes larger components like entire layers or heads. While unstructured pruning can achieve high compression rates with minimal performance loss, it leads to sparse weight matrices that are not well supported by common machine learning frameworks. On the other hand, structured pruning, though it may not compress as much as unstructured pruning, is more compatible with popular deep learning frameworks and hardware. Neural architecture search, NAS, is a method that automatically finds efficient neural network architectures by treating it as an optimization problem. To reduce the computational cost of NAS, weight-sharing-based NAS first trains a super network containing all possible architectures and then searches for the best subnetworks within it. We propose using NAS for structural pruning of pre-trained networks to find subnetworks that maintain performance after fine-tuning. Unlike traditional pruning methods that rely on fixed thresholds, NAS allows for a multi-objective approach to identify the best subnetworks that balance model size and performance. This automation streamlines the compression process and helps us select the optimal model without the need for multiple rounds of manual tuning. Our work focuses on the synergy between NAS and structural pruning for compressing PLMs post-fine-tuning. We introduce different search spaces for pruning transformer-based PLMs and compare them with existing pruning methods. Additionally, we provide a benchmarking suite for multi-objective NAS and conduct a thorough study on standard and weight-sharing-based NAS methods. By leveraging NAS for pruning fine-tuned PLMs, we aim to drive the development of more efficient neural network architectures in the future. Our approach offers a practical use case for NAS in the context of PLMs and demonstrates competitive performance compared to existing structural pruning methods. Section Summary. In this section, we explore the challenges of deploying pre-trained language models, PLMs, like BERT or Roberta for inference due to their large parameter count, demanding GPU memory, and high latency. We introduce a novel approach that combines neural architecture search, NAS, with structural pruning to compress PLMs after fine-tuning on downstream tasks, aiming to minimize performance deterioration. By leveraging NAS, we automate the compression process and identify the Pareto optimal set of subnetworks, offering a more efficient way to select models that meet specific requirements without the need for multiple rounds of pruning based on fixed thresholds. Section: Structural pruning via neural architecture search. In this section, we provide a multi-objective problem definition for structural pruning of fine-tuned PLMs via neural architecture search. We then explain how we can use weight-sharing-based NAS. Finally, we introduce 4 search spaces for pruning transformer-based architectures, each showing a different level of pruning. We start by considering a pre-trained transformer model with L non-embedding layers, where each layer consists of a multi-head attention, MHA, layer followed by a fully connected feed-forward, FFN, layer. The MHA layer processes an input sequence X of length n and token embedding size D_, model, using weight matrices. The output is computed using layer normalization. The FFN layer applies a nonlinear activation function to compute the final output with a residual connection. We define binary masks for each head in the MHA layer and each neuron in the FFN layer. These masks determine which parts of the network are active during computation. We introduce a search space containing different configurations to define possible subnetworks extracted from the pre-trained model. A function called text_createMask maps each configuration to binary masks. We also define functions to evaluate the validation error and the total number of trainable parameters of a subnetwork based on a given configuration. Our objective is to solve a multi-objective optimization problem where there is no single configuration that optimizes all objectives simultaneously. We aim to find the Pareto set, which consists of configurations that dominate others in at least one objective. To solve this problem, we can use standard multi-objective search methods like random search, where each evaluation involves fine-tuning a subnetwork initialized with pre-trained weights. Advanced strategies like multi-fidelity NAS, such as Mo-Asha, can also be employed to speed up the search process. Section Summary. In this section, we define a multi-objective problem for structurally pruning fine-tuned PLMs through neural architecture search. We explain the application of weight-sharing-based NAS and introduce 4 search spaces for pruning transformer-based architectures with varying degrees of pruning. The process involves creating binary masks for each head and neuron in the model, defining a search space of configurations, and optimizing multiple objectives to find the Pareto set using methods like random search or multi-fidelity NAS. Section. Weight-sharing-based neural architecture search. In this section, we present our weight-sharing-based neural architecture search (NAS) approach. It consists of 2 stages. In the first stage, we treat a pre-trained model as a super network and fine-tune it for the downstream task. We use different super network training strategies to prevent subnetworks from co-adapting. The second stage involves using multi-objective search strategies to find the best subnetworks. When training the super network, we update only parts of the network in each step to avoid co-adaptation. This approach helps us efficiently evaluate different subnetworks without the need for multiple fine-tuning runs. By training a single set of shared weights in the supernetwork, we can easily evaluate different subnetworks with just one pass over the validation data. To select subnetworks, we apply specific functions to the shared weights of the supernetwork and compute the validation error. This reduces the computational cost significantly. We can use various multi-objective approaches to find the best subnetworks. The search space theta defines the subnetworks of the pre-trained network architecture. We propose different search spaces with varying levels of complexity: small, layer, medium, and large. Each search space has its own characteristics and influences the distribution of parameters in the supernetwork. By sampling configurations uniformly at random, we observe that each search space leads to a different distribution of trainable parameters. The small search space tends to favor smaller networks, while the medium search space leans towards mid-size networks. The layer and large search spaces provide a more uniform distribution over the number of parameters through a specific sampling process. Section Summary. In this section, we present a weight-sharing-based neural architecture search (NAS) approach consisting of 2 stages. First, fine-tuning a pre-trained model as a super network on a downstream task, and second, using multi-objective search strategies to approximate the Pareto optimal set of subnetworks. By training a single set of shared weights in the supernetwork and updating only a subset of subnetworks in each step, we aim to avoid co-adaptation of subnetworks and reduce computational costs. Different search spaces are proposed to define subnetworks, each with varying levels of complexity and biases towards network sizes, influencing the distribution of trainable parameters during supernetwork training. Section. Experiments. In this section, we assess various neural architecture search (NAS) methods for structural pruning on 8 text classification tasks. These tasks cover areas like textual entailment, sentiment analysis, and multiple choice question answering. Each task has a training set with labels, an evaluation set, and a test set without labels. We split the training set into training and validation sets, 70%, 30% split, and use the evaluation set as the test set. We fine-tune every network for 5 epochs on a single GPU. We employ BERT-base, CAST, and RoBERTa-base as pre-trained networks with specific layer, unit, and head configurations. Despite being relatively small by today's standards, these networks perform well on the tasks and allow for a comprehensive evaluation. We also compare these results with quantization in the appendix. Next, we evaluate different multi-objective NAS approaches on our benchmarking suite. We measure the performance of each Pareto set using the hypervolume metric and report the regret compared to the best possible hypervolume. To compute the hypervolume, we normalize each objective and use a reference point. We assess each method with 10 different random number seeds. We then compare different search space definitions using weight-sharing based NAS. The small search space generally performs best across datasets, except for one. The medium search space, despite allowing more detailed pruning, leads to inferior results due to parameter count distribution. The layer search space often outperforms the medium and large spaces but falls short compared to the small space. The large search space is challenging to explore with random sampling due to its size, so we focus on the small search space for further experiments. We also compare various multi-objective search methods for NAS, including local search, random search, regularized evolution algorithm, expected hypervolume improvement, and MO-ASHA. Results show that random search can be a strong baseline, outperforming more complex methods in some cases. The performance of these methods varies across datasets and tasks, with some methods converging faster or performing better on specific datasets. Section Summary. In this section, we evaluate various neural architecture search (NAS) methods for structural pruning on 8 text classification tasks, such as textual entailment and sentiment analysis. We split the training data into training and validation sets, fine-tune the networks for 5 epochs, and use BERT-base and Roberta-base pre-trained networks. By comparing different search spaces and NAS approaches, we find that the small search space performs best across most datasets, with random search, RS, surprisingly outperforming more complex methods like EHVI or MO-RE on these benchmarks. Section: Weight-sharing based neural architecture search. In this section, we explore different techniques for two-stage neural architecture search, NAS, focusing on weight sharing. We start by evaluating strategies for fine-tuning the super network. We compare methods like standard fine-tuning, random sampling, linearly increasing the probability of sampling, using the sandwich rule, and knowledge distillation. Results show that combining the sandwich rule with knowledge distillation yields the best outcomes. Moving on to multi-objective search, we compare various methods and find that random search, RS, is a strong baseline, while expected hypervolume improvement, EHVI, performs well initially. Using shared weights of super networks for evaluation reduces observation noise compared to fine-tuning each subnetwork individually. Next, we compare our approach to other structural pruning methods. We consider methods like head pruning, HP, retraining free pruning, RFP, layer dropping, LD, standard NAS, SNAS, and weight-sharing NAS, WSNAS. Results show that NAS methods perform competitively with structural pruning methods, especially for larger datasets. Even simple methods like layer dropping can yield good results in the search space. Overall, NAS methods show promise in handling high-dimensional spaces and larger datasets effectively.